We got Alon, Eugene. Everybody's here. Yeah, let us know in the chat. Where is everybody joining us from? So I'm in London. Alexi, where are you this month?
In Amsterdam,
Amsterdam this month. Cool.
as usual, almost usual.
think
Welcome, Tanya. Nice to see you again. Welcome, Todd. Mikhail. Welcome, Larry. I'm happy to see seasoned contributors. Welcome, Mert, JK, Eldad, Dari, Ellen. Nice to see you again.
So what have we got? We've got Russia, we've got New York, we've got the Bay, we've got Vancouver, we've got Israel, we've got all over the place. Berlin. Yes, we've got Europe is well represented. We'll give people maybe 1 minute more and then we'll get on with it. And Alexi will probably have some questions for you, so you'll get a chance for some interactivity. And maybe if Tyler's feeling nice, you can have a prize as well. We'll see how we do. Yeah, change your your send chat to everybody if you haven't got it on the chat widget. I normally take the questions, so you can either write them. If you're on YouTube, you can write them in the chat. If you're on Zoom, also you can write them Q&A, you can write them chat, whichever you want, and then wait for some sort of space where I can ask Alexi, and then we do it like that.
Indeed. And
Cool.
and just so you know, we are indeed also live on the YouTubes at the same time. So if there's someone who's not watching that you think should be, and more people should be learning what ClickHouse is up to, please share that with them. And I'm going to keep a live tweet thread going in the background here on I guess Tweet X, whatever they call them now. I'll keep a live thread of that going on X. So I'll share a link to that. If you have a chance, please do share it with others. So with that said, we're live. I think Mark and Alexei, at your leisure, please feel free to take it away.
Yeah, let's go for it, Alexi. I'll turn my video off now.
Let's start. So this is ClickHouse release 25.2. ClickHouse February release. And we will have about 45 minutes for new features. We will have a guest talk for a secret presenter that we will have today. I will introduce him later. And hopefully a few minutes for your questions. So we have 12 new features, 15 performance optimizations, and 72 bug fixes. So let's start with something small, nice, and neat. And the first one is support for subcolumns in default expressions in tables. Let's suppose you use the new JSON data type, and you have a table with the main column of this JSON data type and a few columns that you would like to extract from this main column. Like in this example, the column time is extracted from the data by this key. And it is already possible. You just write default get subcolumn data and the name of subcolumn. But it is not as convenient as in the version 25.2 when you just write it in the most natural way. Default data dot created at. And you can combine, you can use multiple subcolumns with multiple levels of nesting. And it works. And it is just a small improvement, but it is great for user experience, for usability. And I like these small improvements. The next one is a little bit more complex. It is a way to create copy-on-write storage policies. What does it mean? In ClickHouse, you can specify a storage policy to store data on external file system, even on blob storage like S3. And for these virtual file systems, you can also use read-only file systems like HTTP or HTTP servers with static data. You can prepare a table, export to an external CDN, and serve this table from this CDN. And in this example, I define a storage configuration with a disk named web, which means a web server, and it will point to a GitHub repository. And this GitHub repository contains a few hundreds of megabytes of data in ClickHouse format that you can attach instantly and query. And it was already possible, it was already working, but now the new thing that we have in the new release 25.2, you can define multiple disks from which you have a few read-only disks and a few read-write disks. Like in this example, I would say you base your table on a read-only disk, but also specify a default disk that will contain modifications to this table. So what does it give? You attach a snapshot, but this snapshot is writable, and the writes are performed locally and written to the writable disk. The read-only data is not modified. Let me try to demonstrate it to you. So I will copy-paste some queries first into ClickHouse local. Let me run ClickHouse local. And I will attach a read-only table from GitHub. It works. The count is correct, 27 million records, and it did not take a lot of time to attach, just 1.5 seconds. I can query it, and I don't use any servers. I will use just my resident connection to read this data. A few hundred megabytes is not a problem. So interesting if it will be fast. It is kind of okay. It is working. Reports are being generated in a reasonable time. But if I will try to insert something into this table is about property prices sold in the United Kingdom. And I will try to insert a new record with a price 123,000 pounds sold on January 1st this year. And it will tell me I cannot do it because the storage is read-only. But now let's take a look. Let me run ClickHouse server on my machine. Here it is. And I defined a storage policy with 2 disks. Now I will connect to the server and attach this table with a specific storage policy. And it is even faster. I hope it will work. It works. And the difference is I can insert this record and it is inserted. And hopefully I can show that it is inserted. Yes, it is. No surprise here. What is also interesting is that if I run the optimized query, it will suck all the data in and put it on the local disk. Let me try. it will just read the remote partitions and write them into local disk. And now the same query works in 0 time because the data has been moved locally. Okay, it was not too complicated. And by the way, there is also a feature allowing you to instantly branch any table that you have. If you have one table, you can create another specifying clone as existing table. And that's it. You can modify this branch without affecting the existing table. Okay, yet another feature. Maybe it will be slightly more difficult to explain. It is for attaching tables that are located outside of any databases. So let's take a look again. How do you attach a table from an external disk? When you create this data set, it has to contain the same directory structure as if the table is located inside the database. So it looks like this. There is a subdirectory named store, and in this subdirectory, there are first 3 digits of a table UUID, and then there is UUID. And the reason is because the atomic database engine, that is the default database engine in ClickHouse, stores the data in exactly this directory structure. And when I attach the table, it has to expect the same directory structure. So I have to specify the same UUID. And the path will have to contain these subdirectories. It works, but probably it is not so convenient. In the new release 25.2, it is unnecessary. You can just take the directory for the table itself and attach it directly. It is controlled by this new table level setting, table disk. You set it to 1, and then you don't bother about these subdirectories and just reference the table directory. And it is much more convenient, and you don't have to specify UUID. It's quite a small change, but it will make a difference. And yet another feature, a new output format. Name it JSON compact each row with progress. This format is needed for streaming the data and events over HTTP. So when you receive the result, you will receive chunks of the result in records, and you will also receive events about progress of query execution. You will receive events about additional fields like totals if you query with totals, metadata about column names and types, exception if an error has happened. And it is very handy if you want to implement something like a progress bar in your web interface. And actually, we already have these formats since version 25.1. JSON each row with progress and JSON strings each row with progress. And in the new release, we just added 2 more, JSON compact each row with progress. The difference is compact. Let me show what does it mean. So it looks like this. You query your HTTP, your ClickHouse server by HTTP or HTTPS. You send a query and receive this. And all the events like progress indication, metadata are all the same between JSON each row and JSON compact. But the data records are different. In a JSON compact, they are arrays of column values. In JSON each row, they are objects with column names and values. It's quite a small difference, but it can make a lot of difference in the traffic or in CPU usage. Anyway, you can enable compression in HTTP, and all the formats will work as well. And yet another small feature for the Postgres compatibility protocol. And here I have to remind you that ClickHouse is a multi-protocol server. It has its own native protocol. It has HTTP REST API. It has gRPC protocol. It works with ODBC and JDBC drivers. And also it has a MySQL wire protocol for compatibility and even Postgres protocol. It is configured by default. You can find it in your configuration under the name PostgreSQL port. And if you create an appropriate user, you can connect to ClickHouse with pSQL or pgcli, and ClickHouse will happily pretend to be PostgreSQL for you. Let's take a look what is the new thing in the new release. In the new release, this protocol supports prepared statements. So this prepare command will create a parameterized query, and execute will run this parameterized query. Actually, we don't need this feature. At least I don't need this feature. But it is nice if some tools can connect to ClickHouse directly and not even being aware that it is ClickHouse. And they will use prepared statements, and these prepared statements will run as usual. Interesting, if you use Postgres protocol or MySQL protocol with ClickHouse, it will be interesting to know. So please write in the comments. Now about performance optimizations. In every release, we have at least a few, but more often a lot, performance optimizations. So let's take a look. The first one is for Parquet data format. And in the new version, by default, ClickHouse will create Bloom filters for every column. So when you export your data, it will contain Bloom filters. And when you query these files, these Bloom filters will be read. And it will be useful not only for ClickHouse if you query your files with Spark, or maybe Trino, I don't know. Every tool, almost every tool, will get the benefits of these Bloom filters. And they will take some space, but often just maybe 5 to 10% of the table size. And actually, let's take a look. What is the difference? So I exported a data set with 100 million records with the new version, and it took 11.1 gigabytes. And in the old version, it was slightly more compact, just 99 gigabytes. So the difference is about 12%. But interesting, what will be the difference in query speed? And here I would like to ask you, Mark, What do you think? What the difference will be?
How much faster is it going to be? I don't know. Let's say, I don't know, 1.5 times.
Okay.
Eugene has got a very good answer. Depends on the query. There's the query.
Yeah, it depends on a query. And this answer is correct, but it is not informative. Okay, here is the query.
That's a non-fun answer.
It will just count the number of records by a specific user ID. It should work perfectly with Bloom filters, assuming they are created and being used. And to be sure, I will enable their usage. And actually, it is enabled by default, but just in case. So first of all, a file without Bloom filters and 0.3, 0.2. I will run it a few times. Okay, 0.207 milliseconds. 207 milliseconds. Now let's take and run the same query on a file with Bloom filters. So I need your answers. Mark, Tyler, Usama. Okay, Mark, what do you think?
Oh, sorry, I'm muted. I say 0.1. Eugene says 0.05. Tanya says 42.
0.1, 0.89.
Nice.
2 times faster, slightly more than 2 times faster. Not bad, but
I'm close for the first time ever.
okay, second chance. I have another query. This
Oh, a
one.
new one. Okay.
It will use string search.
So
Exact.
this one should be slower than the other one?
I don't know. Maybe slower, maybe faster. 0.3, 0.2.
3. Only 8 records coming back. Okay.
Yeah, only 8 records. So I expect that Bloom filter will work just perfectly.
0.1 again.
0.1, you said?
Yeah. Oh no, it's
Any
0.01.
Any more hypotheses? Okay.
Nope. I'm the only one.
Actually, you are
Oh,
right.
close.
Very close. Slightly less than 100 milliseconds. Sometimes slightly more. Okay, so no surprise here. Bloom filters work. Another optimization. Inference of conditions by transitive rules. Sounds scary, right? But let's imagine if you have a table with 2 date time columns, start time and end time, and it is something like call detail records. You call someone, and the start time and end time will be recorded. And everything that you speak will also be recorded. I don't know why, but here is the table. And it is ordered by end time because it is the time of recording. So if you run this query with a condition by end time, it will use the sorting key, obviously. But if you run a query with a condition by start time, it will not use the index. You can actually create a min-max index and it will help. But if you did not, you can actually install the new version and specify another condition that end time is always greater than the start time. And if you did this, from the condition on start time and from this inequality, the condition on end time will also be inferred, and your query will start using the index. It's quite an obvious one, but now we have it. Yet another optimization. No time to explain, I will just show you a picture. Parallel hash join is faster in the new release. And why it is faster? It does not have contention. It uses all CPU cores uniformly. In the previous version, different threads bumped on each other and used just about 50% of CPU time. In the new version, they just use CPU all the time and finish faster. Now about interesting stuff. What are the main features in the new release? And the first one is a new database engine. When you create a database with the create database query, you can specify the engine. The default engine is named Atomic. You don't have to change it. But there are other engines such as MySQL, Postgres for integration with MySQL or Postgres. And now there is a new engine named Backup. And with this engine, you can attach your existing backup without restoring it. So your backup can be in a local file on S3, on an external disk, and you don't even have to copy the data. You can just leave this backup as is and attach all the tables inside the database inside the backup. So in this example, I created a backup of my database default inside a file. And then I just plug it in. Let me take a look. How does it work? First of all, probably I already attached it, but let me take a look. So yes, I attached it as another database. So let me interesting. I created another backup of a single table. Here it is. Okay, it did not take a lot of time, just 200 milliseconds. And now let me check if this backup at least contains my table. Yes, and it does. There is a table named hits.
If you would have multiple tables, is there a way that you can tell it just to restore only one of those, or does it have to do everything?
All or nothing. So if
Okay.
your backup has multiple tables,
You get
all
multiple
of them will
tables.
be restored. But don't worry, it does not take time. So if you need a single table, you just use a single table. It is a good feature request. Maybe we
Yeah,
should.
this is from Vishal, actually, a question on the chat. Just was asking. But yeah, cool.
Okay.
Cool.
So I have the original table hits, and I have a table restored from a backup. And I expect that they should be identical. But they are not identical. Actually, this is my table. And let's try to compare the performance. So first, I will run this query from the original table, and it finished in 118 milliseconds. Now let's run this query from a backup. Mark, what do you expect? Will it be faster? Will it be slower?
Maybe a little bit slower. I don't know, 0.3.
I don't know
No.
why it is faster.
Oh, it's
It-
fast. Is it supposed to be faster?
It is faster. So 33 milliseconds is the minimum. And for 43 milliseconds. I would say the performance should be the same. The
Okay.
data structure is the same. Everything is the same. The table in a backup is read-only. So maybe there will be some difference, but I don't expect a lot of difference. Now, yet another feature. Optimization for Iceberg with partition pruning. Let's take a look. Again, I will run ClickHouse local and try a few queries from Iceberg. And first, I will disable partition pruning and I will run these queries. And again, I run them not on a server. It is just my machine, my residential internet connection from Europe, and it will go to US West 2. So probably not the best setup. It will go to the United States and not to the nearest coast of the United States, but still it should work. And these credentials, they are temporary, so don't worry. Today they are active, tomorrow they will not be active. And this is a query from Iceberg. It does something. It reads 5, 6, 7, 8, 12 million records. Interesting, if I remove this condition, how many records it will read? I expect 100 million records because it is the same, it is based on the same table hits, only from Iceberg. It works. Yeah, 100 million, slightly less than 100 million records. Now let's try the same query, but with partition pruning. So without partition pruning, it was 11 seconds, and with partition pruning, I'm asking the same question. How fast it will be?
So what was it 15 seconds before?
11. So 11 with this condition and 15 without condition.
What's it going to be now? So what does it do? What does partition pruning do again?
It will avoid reading from irrelevant files, irrelevant partitions. If the data is partitioned by event date, actually, I don't know. Maybe it is, maybe it isn't. It will just skip unused partitions.
So this will only be useful if you're doing some sort of filtering. Okay. And this is only getting what, 1 day? 1 day's of
2 days, actually.
14 sorry. Oh, yeah. 14 or 15.
Let's run it. Because I
5
don't
seconds?
know. 6 seconds.
Oh.
So
Usama
yes.
said 2 seconds. Very optimistic.
And interesting how the number of records compare, because the full table is 100 million records. If I filter, it reads just 12 million records. And with partition pruning, it is 11 million records. I would expect more, and I would expect a bigger difference. But the fact is, even if partitions are not pruned, every partition also has internal indexes by event date, so we actually don't read unnecessary data. We just looking for irrelevant partitions and reading some files, but not reading a lot of data. Okay, so this is for Iceberg, and there is not only Iceberg. So if I say Iceberg, first, what will be the second? Data lake format. maybe hoodie, maybe Delta Lake. It is the Delta Lake. And our new feature, or not a feature, I would say just an infrastructure change, is the integration with a library from Databricks named Delta Kernel RS. It is very early, highly experimental, but hopefully we will implement schema evolution, deletions, etc. And what is the difference between Delta Lake and Iceberg? And what is Delta Lake in the first place? And why do we have why do we have to integrate our C++ precious C++ code with a library in Rust? And we have Usama, a software engineer at Databricks, as a guest speaker. So welcome, Usama.
Hey, I'm really excited to be here.
Thank you.
All right, so I guess I'll get right to it, folks. I'll be introducing to you the Delta kernel, and I'll be walking you through the story of how you derive an architecture like ours because it's pretty unique. So, the subtitle is Building a Modern Delta Connector. And before I jump into things, I want to quickly remind you on table formats, right? So you have this concept of file format, something like CSV, JSON, Parquet. And in order to read the table, you just need to read the data. That's it. But something like a table format, that takes a little more finagling, right? You have this concept of metadata files, and you need to first read these metadata files, understand them based on the protocol, and from that, read a subset of data files to get your table state. Now, metadata files don't just tell you about the table state, it also tells you some useful statistics. So for instance, if I have this selective query, right, where I say age greater than 24, the metadata files store statistics on each data file. So based on those statistics, I can see, oh, actually, these two data files, I don't need to read them. They definitely don't have relevant rows. So I can go ahead and skip reading those files, and that'll just make us way faster on table reads, especially in tables that are terabyte, petabyte scale, these massive tables. That's not all. With these metadata files, you get this notion of versioning. You can now time travel, go back in time, say, what was my table like at version 3, at version 4? And for each of these versions, it'll give you a subset of the data files to look at. And of course, with versioning, you get these awesome notions of atomicity and isolation. So needless to say, like as you saw, Iceberg is another table format. It's taken off, and so has the Delta ecosystem. You have so many people looking to integrate and implement the Delta protocol. On the Java side with Flink and Spark and Trino. You have on the Rust side as well with Delta Rust. Python uses Delta through a pandas interface. Everyone's using Delta. And not only that, Delta keeps on innovating. It keeps on bringing new features, things like coordinated commits, collations, variants, etc. But there starts to become an issue. For every new Delta feature, you need to go to every connector and implement that feature over and over and over again. And so you have this emergent N by M complexity. And really, the result of that is a lot of folks in the ecosystem trail behind on the features of Delta. Or, on the other hand, maybe they're keeping up, but they're spending huge amounts of resources just to keep up with all the stuff going on in Delta. The goal here is to have Delta kernel be a thin, narrow waist so that Delta kernel implements all of these new and improved protocol changes in Delta. And the hope is that connectors can just hook into Delta kernel and get all of these benefits for free. and they don't have to worry about learning what the new protocol changes are like in Delta. Now, I did say implementing only one time. We actually implemented twice, one in Delta kernel Java for the Java ecosystem, and once in Delta kernel Rust. And this is for, native libraries like ClickHouse or DuckDB, or folks in the Python ecosystem can create bindings to connect into Rust. Okay, so this is our grand vision for bringing together the Delta ecosystem. How hard could it be to build a library for a table format? Okay, well, right off the bat, we need to read a table format, and that's a little bit more complicated than a file format. We need to read these metadata files. We need to figure them out and implement the protocol. But that's implicit. That's what you have to do to build a Delta library. Okay, so far so good. So let's take a look at who's going to use this. You start off with single-threaded engines, and maybe all they're interested in is just read my metadata files, read the data files, and just get me the final state of the table. But that's not all who's using Delta. And you have this other group of connectors that may want to perform distributed execution, right? Something like Apache Spark just will not accept doing things on a single node. And for petabyte scale tables, you just need distributed executors. Okay, so somehow we need a way for our library to take in metadata files and output some tasks, some chunk that we can send out to executors so that they can go perform the data read and with all of their work together, reconstruct the table. Okay. So we definitely want this unit of execution, this task to be abstract, right? We don't want to expose internal protocol details, but we also want it to be splittable. Well, in fact, Delta's metadata is quite splittable. It's a log structured storage, and within it there's a series of actions. So what we can do is just split up this metadata and send it out to all the different executors, and they can take their chunk, read the correct data files, and perform all the processing needed at the executor. And then together, they get the full table state. So what this looks like in practice, in an API, is kernel's table APIs. Let's take a look here. I can declare I want my table, and here's the path to my table. And given that table, I want the snapshot, maybe the latest one. You can also define the version for that snapshot. And then from there, declare a scan. And the scan is where you declare your schema, right? Maybe I want to project away certain columns. You can add filters. I want the rows returned to match this filter. And this is going to be useful when we're doing data skipping. So when you get these scan files are batches of that splittable metadata. And note that this API, we never had to know the internals of Delta. So far, we're just interacting with it at a high level. I want this version, this schema, this filter. All right, that seems to solve our problem. Okay, next up, performance. Ooh, okay. Well, imagine the world where Delta kernel does it all. Maybe it reads JSON, it reads Parquet, it transforms the data. Well, for something like ClickHouse or DuckDB, where they care about their performance, you don't want to import this library that's hogging all of your memory, that's hogging all of your CPU, and that you have no control over. Moreover, engines implement a lot of optimizations. Maybe they have a really good Parquet reader. Maybe they want to have Parquet in some native in-memory format that they have a lot of optimizations for. So kernel can't implement it all. We need to rein it in. Okay, let's introduce this notion of engine APIs so that engines can provide all of their services to kernel, And kernel will be a really thin layer that just orchestrates all of these resource-heavy operations. So the connector says the high level of what it wants. The Delta kernel dispatches to the engine API, hey, read me this JSON file, read me this Parquet file, and kernel will just orchestrate the operations and transformations that have to be performed. And this is what that engine interface looks like. We want a notion of an expression handler. Given some input set of rows, I want to be able to transform it using an expression to an output set of rows. A JSON handler, I want to be able to read or write JSON. A file system client lets us query, hey, what are the files under this directory? And finally, the Parquet handler, I want to read Parquet. So with that contract, kernel says, if you're an engine and you can give me all of this, then you get the Delta protocol. And this is how you would use it, right? You'd declare your engine, and you'd perform all of the table APIs by passing in that engine, saying, here's the engine that will execute all the heavy lifting. Okay, now we're coming up to a problem. That looks like a lot to implement. Ooh. Do we want everyone to have to implement an expression handler, a JSON handler, and a Parquet handler? If you're not, we also have a solution for that too. The goal is to be, upon introduction, batteries included plug and play experience. So you can just use the default engine and get Delta running. But maybe as you mature and as your needs evolve, you'll want to tune the performance. You'll want to get the most out of Delta. And that's where you can move on to a custom engine, one where you have that custom Parquet processing and so on. Okay, so now we've derived the design for Delta kernel. We've solved all the problems. So let's see how this looks like end to end. And I'm going to show you in the scenario of a distributed execution engine. So you have the driver side, sort of where the command for a table scan is dispatched, and then an executor is just somewhere that can perform processing. So here's the story. I want to scan a table, and maybe I have a predicate, a schema, and maybe I define a version. Okay, well, the connector goes into kernel and says, I want that through the table APIs. Well, the first thing you got to do for a table format is, of course, read the metadata files. So we go and we use the file system client. Hey, what are the relevant files that I need? Okay, use the Parquet handler and the JSON handler to read in the files that are relevant to me. And you'll have these active data files. And these are essentially the Delta metadata. Now, these are made up of a path and statistics. Hold on. Well, if we have statistics, then we have an opportunity for a little bit of optimization. Okay, so let's leverage that expression handler from earlier. Perform these expressions over the statistics and using our predicate, and we get to eliminate perhaps a bunch of files. And this is our files after data skipping. So now we've pruned down our metadata, and remember, our metadata is our abstract splittable unit of work. So we start sending that out to a bunch of executors. Let's look at this executor right here. It receives this abstract metadata, and it passes it into kernel. And the very next step after getting your metadata, you go ahead and read the data. So once again, the Parquet handler, we leverage that to pull out the raw data. But the raw data in Parquet isn't the final form. There's a bunch of stuff in Delta that require transformations. Things like generated columns. These are columns that are generated upon a read. They're not actually stored in the Parquet. Or partition columns. These are columns that are populated using values from metadata, because you don't want to store that value over and over and over again in the data files. So you need a notion of physical to logical transformation. Transformation, that's a great place to use our expression handler. Okay, so we take our raw data, we perform the physical to logical transformation, and you get the final state of your table at this executor. And they lived happily ever after. So note that in this whole process, only kernel had to deal with any of the protocol details. All the connector had to do was send around this metadata, and all the engine had to do was perform transformations, which it would be very good at, read Parquet and read JSON. Cool. So this is exciting. We seem to have converged on a pretty cool design. Who's using it? And in fact, there's a lot of interest to leverage kernel. I'm sure a lot of developers don't want to have to deal with Delta anymore and can just offload it to kernel. So on the Java side, we have interest from Flink. Delta Sharing Server is actively using Delta kernel Java in production. On the Rust side, DuckDB is integrating with Delta kernel Rust. Delta Rust, an existing library with Python bindings, is now leveraging kernel. And of course, last but not least, ClickHouse now supports Delta scans using Delta kernel Rust, and we're actively working together to improve the experience and ship even more features through that integration. So I would love to implore you, if you use Delta in any way through ClickHouse or otherwise, please consider contributing to our open source repositories, either on kernel Java or on kernel Rust. We're always keeping an eye out for external contributors. And just remember, the future is interoperable with Delta kernel. You no longer have to deal with this protocol. Leave it to us. Thank you.
Thank you. Just a single question. Could you please make a similar library for Iceberg?
We'll get back to you on that one. We'll see if Databricks ever decides to do it.
Okay. Now let me take over the screen. Okay, so what else? What else do we have in the new release? And one small thing is an improvement for the embedded web interface. So if you did not know, every ClickHouse server has a minimalistic, on purpose, minimalistic web interface which may be not so feature-rich as many other interfaces, but it comes with every ClickHouse server. So whenever you have a ClickHouse server, you can run it on localhost, you can run it inside your internal network and connect using this embedded web interface. And a small new thing is database navigation. So I use it for my public playground. And here are my tables. And I like this web interface because it is easy to use, it is fast. It works. Everything is just instant. What else? In February, we released a new benchmark named JSON Bench. So what it is? It is a test on 1 billion of semi-structured documents from Blue Sky. We took these documents, loaded into every database with JSON support, including ClickHouse, Elasticsearch, MongoDB, DuckDB, Postgres, and compared a few queries. And the results were quite surprising. It was not surprising that ClickHouse is the first one. ClickHouse is the best. It is always the best. It is what we expected. So it is not surprising. But what is surprising is that no one comes even close. Elasticsearch is 10 times slower. MongoDB is 800 times slower. DuckDB is 3,000 times slower, and Postgres is 6,000 times slower. If you want to, I don't know, if you want to check, reproduce, if you want to object on these results, go to jsonbench.com and send your pull requests. Yet another benchmark, but now it is only for ClickHouse, a benchmark for data formats. Which format is the best for insertion? Which format is the fastest? Maybe Parquet, maybe CSV, maybe JSON, maybe Arrow or Arrow Stream. The choice is really large. ClickHouse has about 70 formats out of the box that you can use for input and output. And now you can also have a definite answer for questions like, what is the most optimal batch size? Is it better to compress data before insertion or not compress? And if you need to compress, what to use, LZ4 or ZSTD? Have you even considered pre-sorting your data before insertion? Everything is available in this benchmark named Fast Formats. What else? We released a new open source product named CubeNetMon, a network monitoring and metering service for Kubernetes. We developed it for ClickHouse Cloud to monitor data transfer, to implement some parts of our product. And obviously it uses ClickHouse for data storage. But we also released it in open source, so you can use it for your own services. Take a look, give a star if you like it. What else? BYOC. Not everyone knows what BYOC means, but those who do probably will subscribe, will sign up for this product. So what it is? It is the possibility to run ClickHouse Cloud inside your VPC. Currently, it is available for AWS. It will be also extended to GCP and Azure. And inside your VPC, you have all the compute machines, all the storage, logs, metrics, and only the control plane, sign-on, and billing are outside. So all data belongs to you. You can use every part of your contract with the cloud provider to run ClickHouse Cloud as you want. And also take a look at the open source roadmap. It is published about 2 months ago. And it is already about 15% of the year. So many items from the roadmap are already implemented. But we have a lot of interesting stuff still to do. What about integrations? In ClickPipes, which is part of ClickHouse Cloud, now you have a Postgres connector. So you connect your Postgres databases from different providers and incrementally synchronize data with ClickHouse for fast analytics. There are many improvements for ODBC driver, Java and Go clients, DBT, Metabase, and Grafana. About meetups. In March, we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meetups in March, and probably even more in all parts of the world. In the United States, in China, India, Middle East, Europe, obviously. I will be on some of these meetups, but I will not tell you on which ones. And if you want to know more about all this stuff, like the official connector for Tableau or JSON bench, or how we implemented the JSON data type, what is BYOC, read our blog. There is a lot of interesting stuff. And now we have time for maybe 1 or 2 questions.
We have a question from a while ago. It's one of your favorite ones. When is there going to be write support for Iceberg?
This year, hopefully the first half of this year.
Okay. Cool. Let me check if I got any more. Status on vector search and indexing.
This is a really great question. And you can watch our previous release 25.1, which introduces performance improvements for our vector index. Or you can watch the release 24.12, which introduces a quantized data type, bfloat16, which allows to do precise vector search at least 2 times faster. Actually, it is more than 2 times faster. You get 2 times better throughput, plus, for some reason, just a bit more. And ClickHouse is successfully applied for vector search by many companies already. What is interesting is that in many scenarios, it is better than specialized vector databases. Specialized vector databases contain optimized indexes, but have requirements on the dataset size, and often they simply don't work for large datasets. ClickHouse works for any dataset sizes.
Cool. I think we've done all. Those are the questions. So I guess we'll wrap it up there then. Cool. Thanks everybody for joining. I guess we'll see you in a month for 25.3 even.
Indeed. And for those of you who joined us, you're amazing. Usama, thank you so much for your time, for sharing us with what you're doing on the Delta kernel side, what you're looking at in the future. It's incredible. For those of you who didn't and are catching this later in the fact, you missed out. You should join us live in the future. And for anyone who happens to read this, go give us a star on GitHub, github.com/clickhouse/clickhouse, so that you can stay up to date on what it is that we're doing at all times. We'll see you all in a month. Cheers. Be well, everyone. Bye.